resistors in series and some resistors in parallel. And we're going to look at how we combine those resistors into one equivalent resistor in each circuit. So the first thing to remember in a series circuit is that the current through each resistor in series is the same. So if you look at the current in the series circuit, it doesn't matter where that current is, it's always going to be the same. And that is as a consequence of the rule of conservation of charge. So charge can't disappear. So the flow of electrons, the flow of charge anywhere in the circuit is going to be the same. So we get the current the same everywhere in a series circuit. Now, as a result of that, we can use that to come up with an equation for the combined resistance of those three resistors. We need to think now about the voltage, the potential difference in the series circuit. So the potential difference across the battery is equal to the sum of the potential differences across each resistor. If we take this as V1 across there, this is V2 across there, and this is V3 across that resistor. So we know that the total voltage across all the resistors, or the battery voltage or potential difference, is equal to the sum of the potential differences across each resistor. So taking that, we can then use the equation. We know that V is equal to IR, so we know that the voltage across the battery, the potential difference across the battery, is equal to the current through the battery multiplied by the combined resistance, the total resistance of the circuit. We know that the voltage across resistor 1 is equal to the current through that resistor multiplied by the resistance of resistor 1. We know that the voltage across resistor 2 is similar, and resistor 3 is similar again. It's just that voltage is equal to the current through the resistor, and remember the current is the same everywhere in a series circuit, multiplied by the resistance of that particular component. So using those equations now, we can combine them by substituting V for IR, V1 for IR1, and so on. So we get IR equals IR1 plus IR2 plus IR3. Now, with this equation, you can see that we've got I on both sides. We can now divide both sides by I. So if we divide that side by I, we divide this side by I, the i's are going to cancel out on both sides, and we're going to end up with this equation. R equals R1 plus R2 plus R3, and that is the equation for the combined resistance, or the total resistance, you could say RT, is equal to the sum of the resistors in series. Now, if we look in parallel, the situation is slightly different. So in parallel, we know that each of these resistors has the same voltage across it, okay? So each of the resistors has the battery potential difference across it, and that's because each of the resistors is connected to both sides of the battery. You can see each resistor is connected to both sides of the battery, so it receives the full potential difference of the battery. So each resistor has the full battery potential difference across it. Now, when it comes to the current flows around the circuit like this, but then when it gets to this junction here, it splits. So we get I1 through that resistor, I2 through that resistor, and I3 through this resistor. So if we remember that the current can't just disappear as a result of conservation of charge, so whatever the electron flow is through this part of the circuit, it has to flow through this part of the circuit as well, so that because of conservation of charge, we can't have electric charge disappearing or being used up, so to speak. But what happens here is, as we said, it splits because there's multiple paths for it to flow along. So we can come up with an equation for that. We can say that we know that I, the total current in the circuit, is equal to the sum of the currents through each component or each branch of a parallel circuit, so to speak, because you might have multiple components in a branch. So I is equal to I1 plus I2 plus I3. Now, we can then, similarly as we did before, we can come up with an equation for this, because we know that I, the total current in the circuit, is equal to the potential difference of the battery divided by the total resistance of the circuit, because we've just rearranged the equation V equals IR. We know that I1 is equal to this potential difference divided by the resistance of that component, or the resistance of that branch, I should say. We know that I2, this current here, is equal to the potential difference across this component divided by the resistance of this component or this branch. And we know that similarly I3 is equal to that. So we can substitute each of these into this equation now, and we get V over R is equal to V over R1 plus V over R2 plus V over R3. And then we can essentially divide both sides by voltage. So if we divide this side by the voltage, this side by the voltage, what's going to happen is they cancel out. And we end up then with an equation 1 over R equals 1 over R1 plus 1 over R2 plus 1 over 3. And that's the equation for the combined resistance of resistors in parallel. And you could put RT there. Okay, so we'll do another video then on how to use those equations.